Assalamu alaikum. Welcome to this new video where we will be starting a new topic, which is which is named that roots of nonlinear equations. So let us get started in this new chapter. In the slide itself, we will be talking about polynomials, root of polynomials, bracketing method, open-end method, and finding all roots. So let's get started first by introducing ourselves to polynomials. So if we want to define a polynomial, the first thing that it says is it is an expression of multiple algebraic terms, and it is also a summation term, sum of several terms containing different power of the same variable. Okay. We actually in our regular day or in usually mathematics, we have actually used many such polynomials. For example, many of us use suppose equations that are like suppose see many of us have used equations like this: ax square plus bx plus c equals to 0. Sorry about the cross mark over here. So we have seen equations like this: ax square plus bx plus c. So this is actually a second degree polynomial. So over here we are giving a rather more general term that the power of n and the subscript of a over here. A is actually a coefficient is shown here, and different coefficients with different powers of x. So the highest power of the equation is the degree of the polynomial. Over here we can see the highest power is n, and after that is n minus 1, and thus goes on till x to the power 0. And these last two terms, they can be rewritten as like this. We really don't need to write the 1 over x over here, and x to the power 0 is also 1. So if we say it like that over here, this part is modified. Other than that, this is the same, that for n power polynomial we say the coefficient is an, and such goes on until that, and hence by the end we get this equation, which is actually the general form of any polynomial. Okay, so we can say that equations like right now I'm going to write sample equations. They might not even exist and could be incorrect. So suppose that I can write an equation like 2x square plus 3x plus 1 equals to 0. Okay, well, in this equation, if we look at this one, the highest degree is 2, so this is again our second degree polynomial. So the highest possible coefficient is a2, which will be 2. The second will be a1, which is over here is 3, so we will write 3. And the last one will be a0, which over here is 1, so we will write 1. Okay, so if we want to say a sample of third degree polynomial, suppose we are given the equation 4x cubed plus twice x minus 1 equals to 0. So as we can see, the highest possible power over here is 3. So this is a third degree polynomial, and hence its highest coefficient is a3, which we can see is the coefficient of, when the value is 3 over here, I can see the coefficient is 4, so we will write it. It is 4. Next step is a2. The question is, what is the value of a2? We can see that there's no power of x, power of 2 is present. Well, actually we can assume that over here there is actually a power 2x is present, only its coefficient is 0, and because it is multiplied with 0 the whole term becomes 0. Hence we can assume that the value of a2 is actually 0. Next up is a1 when the power of x is 1, for example over here, and here we can see the value is 2. And last but not least, a0. Now here's the fact, we see that there is a minus sign over here. When there's a minus sign, it actually also is a part of our consideration, and hence over here a0 will be -1. So this equation is actually can be converted into this part, and actually why are we doing this representation is that it will be later very much useful, and we really do need to understand expression of polynomials based on their general terms. It is actually very important. While we are on the note, I would like to also take the time to explain equations like twice x plus 3 equals to 0. By definition itself, over here we get that this is the x's highest power is 1, and it is actually a first degree polynomial, though in reality this is actually equation of a straight line. Though the chapter actually says that finding roots of nonlinear equations, our objective will be finding nonlinear roots of nonlinear equations as well. But as we are discussing polynomials, one thing for sure, that this type of equations are also possible, but this is not our concentration, to be exact, because as we go on, if I have time, I will show you that in order to find the result or the root of this polynomial, we do not need to go for the extra mile of the like the algorithms we are seeing. We do not need to go that much. Hence this is more concentrated on finding roots of nonlinear equation rather than the linear ones. So let's move on. Suppose when the value of n is 1, that is a first degree polynomial. Here I have given an example, y equals to x plus 2. Okay, so this is actually an equation, and if you are confused, just consider that if I would like to have a connection with the one I showed in the previous page, just think that it is also equals to 0. Okay, now think x plus 2 equals to 0. We have already worked with this type of equations. This is actually the whole same, just that I'm considering y instead of x plus 2. And now if I write an equation like y equals to x plus 2, then we can draw this graph. Okay, let me once again pull it up again, that in the previous page we have written situations like x plus 2 equals to 0, right? So we have written x plus 2 equals to 0, but now I'm just rewriting. If I write this part, rewrite, we can say that x plus 2 equals to y. Okay, now if we draw the curve, you do not need to, we will discuss later why y and 0 are actually in the same place, but you already know how to draw graphs. If we draw a graph of this equation, we will get something like this a straight line over here, and this looks like the same. Now why does it look like this? The main reason is we have previously written, you have previously written f of x equals to x plus 2. You have written previously, I believe. And if you remember that we used to say the value for which value of x the right side is 0 is called the solution of the equation, right? You should have studied this in mathematics courses, that for the value of x that makes the right hand side 0 over here, x plus 2 is 0, is the solution. You should have done that in the math course. And we have also written in some cases that y equals to f of x. So at the end of the day, due to some mathematical reasons that I will not express, it will take more time, that we actually want to make y equals to 0. This is our main objective, when y equals to 0, over here we can see that y is 0 in this line, which is the axis line, and you can easily see that the solution of this equation is when x is -2, and when this equation is drawn, you can see that at the 0 point, that is the x-axis, it's -2 point that actually gets hit by the line. So hence this is purely mathematical topic which we will not do, we will not express, or we will not discuss much about. But if you want to have a good intuition, you do need some mathematical background as why we are doing this, and this is the topic, and hence there is some connection with mathematics as well. So if we write y equals to x plus 2, this is back to the topic, it's a first degree polynomial, and the graph looks like this, and you can see that it crosses the x-axis only in one point, thus n equals to 1, or it has one solution, not multiple solution. When the value of n is 2 and we consider an equations like this, we get a graph like this. Okay, and in this case on the x-axis it actually it's 2 points over here and over here, and thus these 2 points are actually the solution of the equation, and so we get root for n equals to 2. What about n equals to 3? Suppose this equation is given over here, then we have 3 points that actually hit. You can test it by drawing using any mechanisms you know. It actually hits 3 separate points in the graph, and these 3 points are actually solution of this equation. You can try it out. It actually is the solution of the equation, and thus the degree of the equation provides us with some level of knowledge as how many roots are possible of that equation. So let us start our discussion regarding root of polynomials. So what is the root of polynomial? The root of polynomial is actually a solution to the polynomial. We have seen some polynomials, the resultant values which actually solve the equation, they are called the root of that polynomial. Over here I have written what I said earlier, that usually we try to prove that y equals to fx equals to 0, and we try to find the value of x for which f of x equals to 0, which is essentially the same thing as the value of x where the curve touches x-axis. Okay, so there are many methods out there when it comes to solving polynomials, like direct analytical method, which we usually do when we do maths. There are graphical methods. You have done graphs before, as the one I was taking help of. There are trial and error methods, and finally there are iterative methods, which is our main concentration while we will be studying this chapter. So this is what we are mainly looking for, iterative methods. So in iterative method, it is first of all divided in two parts. One is the bracketing method and the other is the open-end method. What is a bracketing method? Let me explain. In a bracketing method, we first have to define a range, and we must ensure that the answer is within the range, and we will search in this space to find the solution or the root of the polynomial. Whereas the open-end method, it's actually just as the name says, it's open. In an infinite number line, we just hold, okay, I will starting from here. Sometimes we will go this way, sometimes we will go this way, but we do not have a limitation that okay, I have to go this way. So this is an open-end method. We search all the way around here and there. Another name of bracketing method is interpolation method, and open-end method is also called extrapolation methods. Among interpolation method, we will be studying two methods, bisection and false position. Among open-end method, we will be studying three algorithms, Newton-Raphson, secant, and fixed point iteration. A good to know intuition is actually there is not much of a difference between the integrated methods, just one line difference. Other than that, the algorithms work almost exactly the same way. So let us get started. In the next slide, we have said n degree polynomial has maximum of n roots. Okay, here we have used the word maximum. The question is why. In the previous slides we have seen, I have showed that the number of n is the number of roots available. Well, then what's the problem over here? Well, consider situations like x square equals to 0. Is this a valid polynomial? Yes, it is of course a valid polynomial. Then if this is a valid polynomial, what are the possible roots? There's only one possible root, that is x equals to 0, but this is a second degree polynomial. According to definition, it should have two solutions, but over here it has only one solution. It's mainly because the solution is like this of this equation. Solutions that are like this, that actually just touch the x-axis, for this type of scenarios we will get, instead of 2 points we get only 1 point. This type of equations are like these ones, they are like this, and hence the maximum words needs to be used. There can be lesser ones, but it cannot exceed this number. The maximum number of possible roots is n, and thus comes our next part. Okay, so in the previous slide I have discussed two stuffs, bracketing method and open end method, and I have said one thing: one needs a range and the other needs an initial point to start up. Now actually when I say a range, I actually meant a starting point and an ending point, and when I say open method I mean just a point. So we have to start off somewhere, we have to make some initial guesses to where to start for. So hence we have two equations. We will not go to proving the equation. One equation is this. Over here they give an initial guess. You can see the value of a n minus 1 and a of n is required. Hence that is why we have already studied on expressing polynomials using the general terms. So using this we get a single point of guess where to start off. And over here there is a larger equation, and as you can see there is a square root over here, and as we know every square root adds a plus and minus sign before the equation. So we actually, if we get suppose plus minus x as the answer of this equation, we can say that the solution lies between plus x and minus x. I think I missed the signs a little bit. It should be from minus x to plus x if I follow the arranging convention system. Okay, so this is the expression. Over here we just got a range, and over here we got a point to start off with. So these two equations will be needed for our next part. And another thing is, numerical method is all about approximated solutions. That is, I cannot say that if the answer is 2 I will always get 2. Sometimes I may get 1.98, but sometimes it may be the case I'm not satisfied with getting 1.98. I need more accurate results. So what should I do? I need to say that I am satisfied if I get something like this. So how we parameterize, or how do we get this? Well, the secret lies between the error threshold. We will provide our system or our code a threshold or a tolerance limit, that I will accept the code if it has suppose 0.0001 error, then I will accept the answer. So this can be given to the code using the error threshold. How it can be given we will show it later, and if the error is within range then we got the root. You can stop searching for the root. Other than that, otherwise update the guess using an equation and try finding the root. So this is the very general method of iterative method to find the root of polynomials. We will do exactly this procedure over and over again while we are at this topic and this chapter. So we will continue on working on this same stuffs over and over again. Okay, now we have talked about the error threshold. Error threshold can be of different types. One can be the absolute error. While the absolute error, as we have discussed earlier, is actually a difference between xi1, and here what the I represents is, we have talked about iterative method. So I plus 1 actually means the iteration number of the loop. So we can determine the absolute error by differentiating, by calculating difference between two successive root guesses. and if we find that the root case is smaller than the error threshold, then that is the answer. Another way can be just by dividing the x by I plus 1, we can get the relative error. Now one thing I want to tell you, that our objective is always to find that f of x equals to 0. This is actually our main objective, to make the f of x 0, which actually we cannot do, we are bound by limitations. So our main objective is make f of x is approximately equals to 0. Okay, this is actually our objective. But why are we stopping here, absolute error and relative error of x itself? Well, the answer lies in understanding the algorithms first, which I cannot experience right now, and hence I will tell you through. Stay tuned for the later parts, so we can actually explain why is the difference and relative error of the guess is enough. Well, over here is actually what we are trying to get. We want the value of f of x plus 1 to be 0, and hence the value of it as less as possible is acceptable. Or we can also find the difference of the successive guesses. Well, it is actually related to why we are using the previous two. And honestly speaking, in my experience, if I have to share, I've seen most cases use this system, and some cases some special conditions arise when you have to use this one, but I have not seen much use of these two ones at all. Usually these two work it out well, but yeah, they are not actually complete garbage. Sometimes we may need these systems. So these are the stopping criteria, and what does the stopping criteria do, we will understand it much better when we start working with the algorithms themselves. Next comes Horner's rule. Okay, so let us consider an equation, 2x square plus 5x plus 6 equals to 0. Suppose this is an equation given. I don't know if the equation is correct or not. This is just a sample. Okay. Now in computer science, if I want to consider here, it is an x square, so x and x will be multiplied. Okay, let's break this down, so make it a little bit easier. So over here we can see there's 1 2 3 multiplication operations, plus we can see there's 1 2 addition operations, which equal to make it a 5 operations in total. Okay, now if we just write the equation like this, twice x plus 5 into x plus 6 equals to 0. Now see, over here we have one multiplication operation, we have one addition operation, over here we have another multiplication operation, so 1 2 3, and over here 1. So we have a total of 4 operations happening, which is less than the number of operations here. What's more important is if I add just another term over here, suppose x cube, only just x cube. Okay, so if I just add an x cube over here, we get an additional addition operation and two multiplication operations. So 1 2 and 3 are added, so 5 becomes 5 plus 3 8 operations. But if we express the equation using this mechanism, the equation becomes x plus x plus 2 into x plus 5 into x plus 6 equals to 0. If you watch carefully, okay, this equation is exactly same as the equation given here, but the number of operation over here, one addition, one multiplication, one addition, one multiplication, and one addition. So 1 2 3 4 5, so only 5 operations, whereas over here we had 8 operations. So in the sense of algorithm or a computer, this is a costly operation, this is a less costly operation. Though the equation may look a little hazy in human eyes, actually for computer this is a much better operation, and this is a costlier operation. This is what Horner's rule is. This is a systematic way for expressing equations to make it less complex, and this is the Horner's rule. Over here we have written the Horner's rule pseudocode, and hopefully we will try seeing this code in action as well sometime in the soon. But this is the pseudocode of how Horner's rule can be used to calculate the answer. So that is it for this video. Thank you very much for staying tuned. From the next video on, we will start discussing about specific methods like the bracketing method. Thank you everyone. Let's see you in the next class. Assalamu alaikum.